gonna riff on the idea of divide and conquer. A divide and conquer is a motherhood issue. Yes, it's a good idea to do divide and conquer, but I don't think it's being done enough. So how to achieve divide and conquer? Well, one is we want to minimize data. Another possibility for that is to assume that everything is a fractal. Everything breaks down into two parts. One is there's a what I call a leaf and what I call a composite. And every composite breaks down into further leaf and composite. So that's 50,000 foot level idea of how divide and conquer works. How do you accomplish that? What do we need to achieve divide and conquer? We need isolation. And many people talk about encapsulation. But encapsulation is not enough. It leaves out, it omits control flow. Object-oriented does encapsulation. The first time it became popular was when Smalltalk was introduced. There were things that came before Smalltalk, but Smalltalk brought in all the ideas. One way to encapsulate things and include control flow is the Unix philosophy, Unix processes in the pipeline, is that Unix processes give us isolation. Smalltalk gives us encapsulation but omits control flow. On the other hand, the process model is like a sledgehammer. Something that needs to be explored is the idea of closures, or explored further. We have closures. Do they give us isolation? Can we employ them for isolation? The ideas for closures have gone to continuation passing style, and the problem with continuation passing style is that it is the ultimate, it's the ultimate go-to. Another way to achieve divide and conquer is to use layers for everything. So there's layers for development, layers for data. So let's look at development for starts. So what we've learned in other disciplines is that development should be divided up into a number of sub-disciplines. Architecture, engineering. Engineering is not coding. It's providing details. There's implementation is coding, and then there's Q&A, there's or testing, maybe there's deployment, where deployment breaks down into regression testing, actual delivery, There's sort of rebuilding the system, versioning. These are all aspects of deployment. Aspects of architecture. So all of these things are associated with development. Well, let's look at engineering. You can do, there's realization. So whatever the architect said, let's just make it work that way. Then there's optimization. There's UX. There's security, locksmithing. All of these are parts of engineering. Architecture likewise has a UX component, a general design component. We don't worry about optimization in architecture. We leave that to optimization engineering. An engineer who's good at optimizing things will first we'll get an engineer to just make the thing work. Then we get an engineer to optimize the thing that works, and that kind of engineer will look at the code and decide whether there's general refactor, or there's maintenance. What is that? That's not even deployment. That's kind of, where does that belong? Maintenance. One needs to refactor for maintenance. There's DRY that belongs to maintenance. We'll notice that DRY, repeat yourself, is used in architecture, but DRY is really an idea behind maintaining the code, making it better. Again, you chop that up into little pieces, into a layer, a maintenance layer, then the architect doesn't have to worry about it, and can basically just design what he needs to design, express it in some form. He's got to have some form to express it in. So in traditional architecture, we take a blueprint, and the engineer also gets a blueprint, creates a blueprint, and he hands that blueprint off to implementation. The architectural blueprint, well, it's more like let's not dignify it with the word, it's more like a design drawing. So the architecture comes up with something like a design drawing. The engineer looks at the drawing, fills in dots all the I's, crosses all the T's, fills in missing cases, and so on, and then produces a blueprint of how the thing should be implemented. He hands that blueprint off to the implementer. The implementer team then codes up the solution, and they may need to go back to engineering and say there's pieces missing here, we need to stop and think. The implementation should happen at the speed of typing, so you should be able to touch type and just look at that's the goal of implementation. Currently that's not the way it happens. And currently we expect developers to do all of these roles. Basically all of this stuff is done by one team of developers. If you divide the team of developers up into people who have experience with lots of different paradigms, they might be called architects. Then there's engineers who are very detail oriented and figure out how to make things work. There's also research, R&D. So there's for a specific problem. general R&D, and these two things. So if you look at what we ask developers to do right now, they're doing just about everything under the sun. We can try to divide them up. So junior coders, ones who understand different languages and figure out the ins and outs of particular languages, can be implementers. Engineers can be detail-oriented people. They don't need to do coding, but they do need to create blueprints. At the moment, we don't have a blueprint technology. I'm suggesting diagrams and I will show in a different talk how to how to transpile diagrams into code. An architect also comes up with some sort of diagram or drawing or some way of communicating to the engineering team what needs to be done. The architect explores the problem space. Physicists do that also. The way physicists work is they come up with a notation to express the problem, and then they use that same notation to express or to invent a solution to the problem. And an example of that might be Feynman diagrams. Took out all the details and drew diagrams of what he wanted to think about, and then he used the same diagrams to think about the problems and to come up with solutions to the problems. In many ways, this is sort of an architectural kind of thinking. We would have thought that physicists go under R&D, but in this particular case, what I'm talking about is the way to layer, the way to divide and conquer a problem into first use divide and conquer to find a notation. So divide and conquer consists of find a notation is one. Next step is express the problem using the notation. Think about the solution, and then express the solution using the notation. Again, none of this stuff happens in one fell swoop. As we think about the solution, we may find things that affect the notation, and we'll go back and modify the notation and come around and modify the problem with more detail and so on. And what we're really doing is this business here. We're fractalizing a problem. So we're taking a piece of the problem, we figure out what to do with it, how to solve that piece, and the rest we leave alone. And later we come back to the rest, or mentally, not even later, we can jump between solving a piece of the problem and solving the bigger problem. And what we do, we end up breaking down the problem into a leaf and a leaf node and a composite node, and then we keep doing that over and over and over again. That's what we're doing here. So we think about a solution. If we find that our thoughts need to modify the notation, then we modify the notation. We come back, we fix up the expression of the problem. We continue thinking about the solution. When there's no more things that we want to add to the notation, we start to think about how do we express the the solution using the notation, and once we've got that, then we can stop solving that particular leaf problem and go on and find another and break down what's left into more pieces. Something else we want to do to achieving divide and conquer is to normalize, let's say, everything we can normalize. Can we normalize the data? Can we normalize the control flow? We've already, believe it or not, we've already looked at how to or as a profession, we have figured out how to normalize control flow, and it's called assembler. And if we look at assembler, it's normalized into triples. And the triples are an instruction and operand 1 and operand 2. And in fact, there's better names for that. Let's call it a relation and a subject and an object. So when we say move R1 into R0, we're basically looking at a relation subject-object. We can do the same with data. And again, here we want to do the same thing. I want to go back to triples. Often appears like this: relation, subject, and object. Or that's the way it appears in prologue. In Lisp, we would say relation with no commas, subject and object, and no dot at the end, and that would be Lisp format, Lisp or scheme format. And say in JavaScript, we would say relation subject and object. And in general, we would say relation subject object all in one line. So that's what we really want to do. And when we do this we break data up into triples, I call it a fact base. Something in this format is a fact base. If I go back to layers, I can also think in terms of time. Traditionally, we break things up into two kinds of time. There's compile time and there's runtime. And that's actually a little bit of a lie. What we really do is we have compile time, and then we break runtime up into two parts, which is load time and I'll call it steady state. That's a state machine term. So runtime breaks down into two things. And in compile time, what we found is we do type checking, and we do code emission. Let's go back to processes. Well, in fact, processes, threads. Let's call it threads. And threads are really Unix processes are in fact a kind of thread, and a thread itself is a sledgehammer approach to things. So I'll take that out of here, put that over here. And one of the problems with threads is thread safety, which is really, it's an accidental complexity, and it's due to the idea of memory sharing. And it turns out that memory sharing is itself an epicycle that we've added to make things harder for ourselves. You don't actually do memory sharing in a properly concurrent system. A properly concurrent system consists of multiple computers. Each computer has its own CPU and it has its own memory and thin wires that connect them. And we don't share memory between the two types of computers. So all of this stuff from here down, thread safety, there's no such thing as thread safety. It's an accidental complexity that we've added to the problem ourselves. Let's talk about minimizing data. The best way to minimize data is to restrict data flow. Minimizing data, we want to put the data into layers. I've set that up here. I'm going to delete that one from there. And how do we put, well, that comes into scaling. And scaling turns into the problem of parent-child structuring layers. And I propose a law that says the parent, well, in fact, I should have probably broken this up into two different parent or child layers. I'll leave that. So there's a parent and there's a child. So what can the parent do? The parent can one, it can command the child to perform an action. It can receive information from a child, and it can pass information. It can filtered information. Let's put it that way. Info to parent of the parent. There we go. So the parent does that, or that, or that. A child can perform an action when commanded. It can, well, there we go. It can send, maybe filtered, send information to parent, and that's about it for a child. These two belong up here, and basically in all cases a parent is a composite. No, wrong. A parent is always a composite, and a child might be a composite, or it might be a leaf. We don't know, well, in fact, what we'll say is, let's say it's a part or a component. A child is a component, and it could be a composite or leaf, and a parent is also a component. Can I do this? Bang, yes, there we go. A parent is a component, but we know because it's a parent that it's always a composite kind of component. If we look at restricting data flow, the goal would be to have exactly one input and exactly one output. We can see that functions and libraries fall well short of that goal. Message passing, on the other hand, so I'll put libraries aren't very restricted. They have many inputs, and then they have hidden dependencies, and then they have say one output. Let's just say that's the case. Again, so they're not very, so libraries don't actually satisfy this constraint of restricting the data flow. What does restrict the data flow is message passing. Message passing can call send, and it can, in essence, receive. I like to put spaces between my parentheses. So message passing does satisfy this goal. The one problem with message passing is that it's usually done as a flat system, and that usually leads to failure. There we go. Failure. The trick to doing that, though, is to use hierarchical hierarchical message passing, and then that starts getting into this parent-child business. I won't show a connection there, but that's a success. That's a path to success. Let's put that in here just as a reminder that if you do message passing in a flat way, it will fail at some point and will not scale. If you do it as a hierarchy, in this kind of hierarchy, then you will get further and possibly succeed in solving more new problems than you could the flat way. A major issue is in performing divide and conquer is defer as much as you can. So can we defer? So how do you defer, let's say, data? So the trick here is to build data structures that only include the information you need at a given point over time. So this is actually a time relationship. Getting rid of time is basically always a bad idea, but that is what we're doing. And here's an example. If you look at this mind map as a whole, it becomes very hard to read because there's way too much detail on it. If you look at this mind map as I evolved it over time, then it becomes a lot simpler or a lot more easy to follow what I was thinking. If we talk about deferring data, then one of the things that enters into is with respect to runtime, load time, and steady state stuff. So one thing the compiler does is it defers some of the data, so some fix-ups are deferred, and they're fixed up at the load time. What we want to do is do that in the extreme. So instead of one big compiler that does everything, we want a compiler that only does the type checking, and then we want to leave the type checked code with a bunch of holes in it saying I haven't done this other stuff, and then we want to pass it to another processor or another thread or process or function, whatever we want to, however we want to chop it up, and then we want to add to the type checked code more information. For example, what we do with the compiler is we do all the type checking, and then we do the code emission. Can we chop that up even more? I certainly did that with an Eiffel compiler. The Eiffel compiler type checking was much more difficult than it was, say, for a C compiler. In Eiffel, it was checking classes and walking class hierarchies to see if things hung together correctly. And it tried to do all of that in one fell swoop, ended up hitting the disk an awful lot and slowing itself down. One way to break out of that was to break up the type checking into phases. So what can you type check given the source code? Type check the source for a single file, and then you can break that up into type check the system. We tend to lump both of these together, and that's what was happening in the Eiffel compiler. And the way I broke it up was that I just slit the compiler into two passes. One that looked at a source file and said, what type information can I glean from this source code? And all this other stuff is, I don't know, but I know I'm going to need it. So I left tidbits in the, let's call it a .o file format, or an intermediate .o file format that went from here. It created an intermediate .o, and then it went to here and created a full-blown .o, and then that full-blown .o went to the load time. And that is the type of thinking we need to apply to everything that we code up. Do we need to know everything in this data structure at this time, or is there something we can leave alone? Is there something we can know from the structure of the file that we're reading, and we can fill that in, and the other stuff we just leave alone for another pass to handle? And that's the Unix mentality, is do one thing and do one thing well. And that we need to apply that kind of thinking over and over and over again in layers as we build a system. So at the moment we have only two layers. We have the source code for a system, and we have the big flat compiler for the system. And that's the way we also design languages at the moment, we stick things like plus and minus and times and divide operators into a language, but we don't actually need them at every step in writing the code. We can write code without plus, minus, times, and divide, and then pass it on to another layer that says, for example, let's say we write everything as a function, and so we say, I want to add these two numbers, but I'll leave that as a function to be resolved later in a further pass. And then further down into the implementation, we would then resolve how to add two numbers, and that would be done with a language that allows us to, worry about the details of adding two numbers together. The details are kind of things like, is it a float, is it a double, is it a big num, and we call different kinds of libraries for each of the kinds of things.